Welcome to Hart and Trocken. In this video we are going to talk about number systems and their relevance in our way to introduce complex numbers. The story about complex numbers starts with a story about number systems and their extensions. So what does that mean? Let's first understand that mathematics is not limited to real-world observations. So unlike chemistry, physics, biology or medicine, mathematics is not limited to things which can be observed in the real world. That gives much freedom to mathematicians to create new concepts, objects and ideas and integrate them in the existing mathematical world. However, that freedom doesn't mean that anything is possible, but that this anything must prove valuable and consistent with the existing concepts. Logic and consistency are hard requirements. If they are fulfilled, new ideas and concepts become possible. A brilliant example for this are the complex numbers, and we're going to talk about number systems in order to understand the way towards complex numbers. The first number system we're going to talk about are the natural numbers. Natural numbers are the most easy to understand type of numbers. They are the set of numbers given by 1, 2, 3, 4, 5, 6 and so on. They are denoted by a capital N. You see this double strike bar. Natural numbers occur in everyday life, e.g. when counting objects like apples, coins, human beings, and so on. But when doing mathematics with natural numbers, things get limited quite quickly. Doing mathematics in many contexts means to take a problem, a real-world problem, and build an equation from this problem. And the equation should be solved in mathematical terms. Of course, we want the solution of equations to be part of the number systems we are working with. Now, if you work with the natural numbers, we want the solution of an equation to be a natural number. Now let's have a look at very simple equations of the type a plus x equals b, where a and b are natural numbers. One example is the equation 5 plus x equals 7. It's very simple to figure out that the solution to that equation is x equals 2. That's perfectly nice because 2 is a natural number and we're happy. However, the next equation doesn't behave nicely like that. In this case, we look at the equation 5 plus x equals 2. And it's apparent that the solution to that equation should be something like x equals negative 3. Because 5 minus 3 equals 2. However, the number negative 3 is not a natural number because it has a minus sign. That means it is not contained in the set of natural numbers. So already that very simple equation gives us a problem regarding the number system of natural numbers. And one solution to that is to extend the set of natural numbers to more numbers. Obviously, the extension we want to do to the natural numbers is to add the negative numbers as well as the number 0. We call these numbers integers and we denote them by a capital Z. Again, note the double strike bar in the middle. In this situation, using integer numbers, equations of the form a plus x equals b always have a solution in Z no matter what a and b are. The only condition is that a and b themselves are integer numbers. So for instance, if we look at 5 plus x equals 2, we get x equals negative 3 as a perfectly valid solution within the system of integer numbers. So far, so good. But we can destroy that nice picture by simply introducing multiplication as an operation. And again, we will run into similar problems as before. Because now, if we look at equations of the structure a times x equals b, where a and b are integer numbers, we always find bad examples which don't work out in the integer numbers. But let's first have a look at a good example. 3 times x equals 6. Obviously, the answer is x equals 2, and 2 is an integer number, so everything is nice. But looking at a similarly structured function, 3 times x equals 5, we run into a problem. Because obviously the solution to that equation is not an integer number, it's a fractional number, a fraction. So in this case, we have x equals 5 over 3, because 5 over 3 times 3 is 5. So we see that that equation cannot be solved in the number system of the integer numbers. So again, the solution to that problem is to extend the set of integer numbers. So the extension we need to do to the integer numbers is to add all fractional numbers. Fractional numbers are numbers of the structure p over q, where p and q themselves are integer numbers, and where we have the restriction that the denominator of that fraction, that means q, must not be equal to 0. This number system are called the rational numbers and is denoted by a capital Q, and again note the double strikes. So Q contains all numbers which can be written as a fraction. They also contain all decimal numbers, for example 1.456. To see that, we simply multiply a given decimal number by 1 followed by this many zeros as there are decimal numbers. So in our example, the number 1.456 is multiplied with the number 1000, which has 3 zeros, and we receive the number 1456. To redo this multiplication, we of course have to divide that number by the same number 1000. So 1456 divided by 1000 gives 1.456. So the result of that little game is that we have shown how to represent a given decimal number as a fraction or a rational number. This at least is true for all decimal numbers with a finite number of decimal places, something like 1.456. But you know that there are decimal numbers which are called periodic decimal numbers. One example is 1.273, where the horizontal bar over the numbers 273 means that these three numbers are repeated infinitely many times. So this is just a short version for a very, very long decimal number, which is 0.273, 273, 273, 273, and so on. What about these special periodic decimal numbers? We want to understand the question if they are contained in the rational numbers q or not. So is this number an element of q or not? As it will turn out, they are elements of q, no matter how long the period is the combination of number looks like. As long as there is a period, that means a finite collection of digits which repeat themselves infinitely many times in the decimal representation of the number. So there's a nice little trick to show that that is true. Now I don't want to give you the general proof, but I want to demonstrate its core idea with a little example. Let's first take that number 0.273 period and call it x. This is done in this little equation here. Now that being an equation, we perform a little operation on that equation. And this operation is simply to multiply both sides of the equation by 1000. Now what does this result in? Now let's first have a look at the left-hand side of this equation. What happens if I take the number 0.273, and so on, and multiply this number by 1000? What do we get? Well, as you know, when multiplying a decimal number with 1000, the decimal point moves to the right by 3 digits. So this is what we do. We move the decimal point to the right by 3 digits. That results in 273, and now there's the decimal point, and then the story repeats, 273, 273, and so on. So you see what happened? The number itself hasn't much changed. The only thing that has changed is that one copy of that period of digits, 273, is now being placed in front of the decimal point. Nothing changed regarding that periodical part after the decimal point. So to rephrase this insight using the periodic bar leaves us with this number. Looking at the right-hand side of the equation, things are very simple. We just have 1000x. Now there are two equations we end up with. Equation 1 and equation 2. And now let's do a weird little trick. We subtract equation 1 from equation 2. Subtracting means we perform this operation for the left-hand sides and for the right-hand sides. So let's have a look at the left-hand sides. We're supposed to subtract this number from this number. Obviously, the difference is only given with respect to what happens in front of the decimal point. And the remaining difference is 273. The reason for that is that what happens after the decimal point is exactly the same for both of these two numbers. On the right-hand side, however, we're supposed to subtract x from 1000x. So 1000x minus 1x gives 999x. So this subtraction operation leaves us with the equation 273 equals 999x. Now if we simply divide this equation by 999 on both sides, we get a representation which fits very nicely to our definition of the number system Q. So you see, we started with x being this periodic number, and we ended up with showing that the same x has a representation, that means has a way of writing it down, which is perfectly nicely in line how Q has been defined. So at this stage you see that we have extended the original natural numbers, first by negative numbers and 0, and secondly by all fractional numbers. Now the rational numbers which result in these extensions seems to be a perfectly nicely way of thinking of numbers when looking at the real world. It is plausible that we think about negative quantities, for instance debts. If I owe money to someone, we can speak of owning minus 300 euros. And it's also plausible to talk about fractions, like a cake which is being divided by different people. Is there any necessary or even possible extension to the rational numbers? The answer is yes. Again, it is induced by very simple equations. Let's have a look at quadratic equations like x squared equals 4. This equation has two solutions. The first one is x1 equals 2. The second one, x2 equals negative 2. Both of these solutions are contained in Q, that is the rational numbers, and they are even contained in the integer numbers. A second example is the equation x squared equals 9 over 16. For this equation there are also two solutions. x1 equals 3 over 4 and x2 equals negative 3 over 4. However, there is a famous, very simple equation which does not have a solution in Q. And that equation is x squared equals 2. In other words, that means that the square root of 2 is not a rational number. Now, this fact is not immediately clear. It requires a mathematical proof. So let's have a look at the proof of why the square root of 2 is not a rational number. Let's for the moment put ourselves in the position that we have no idea what the square root of 2 is. The only information we have about it is that we receive 2 when we multiply it with itself. Expressed as a formula, that means that the square root of 2 is a number x such that x squared equals 2. And it's just for the sake of clearness or convention that we denote this x by the symbol square root of 2. By now, this is all we know about that number. And it's a common procedure in mathematics to only start with very little information about something new and step by step collect more information and properties. While collecting these properties, we carefully make sure that we only exploit that little bit of information we already know, that x squared equals 2. Now remember, we want to prove that the square root of 2 is not a rational number. How can we be sure about this? In fact, it will take us a couple of logical steps, each carefully put upon the previous one, ending up with the insight that the square root of 2 cannot be a rational number. To this end, we use something which in mathematics is called indirect proof, or a proof by contradiction. For this kind of proof, we assume that the proposition we want to prove is false. And then we will show that this assumption will imply a contradiction. Imagine yourself being at court defending your case. You want to prove that you are innocent and that you didn't commit the crime. One strategy you could choose for doing that is by assuming in the beginning that you did commit the crime. So you assume the contrary of that what you want to prove. Based on this, step by step, you will derive certain implications which will lead to a situation which is obviously not true. So everybody in the audience and the court have to agree on the fact that the implication is not true. So there is only one logical consequence, that your original assumption that you did commit the crime has been false. That is the principle of tertium non datur in Latin, which means there is no third alternative except for either your assumption was true or your assumption was false. So let's begin the proof. As we want to show that the square root of 2 is not a rational number, we start by assuming the opposite. That means we assume that the square root of 2, whatever that is, can be represented as a fraction of two integer numbers p over q. Now the basic idea of this specific proof is based on a simple extra condition which we demand to be fulfilled, namely that the fraction p over q cannot further be reduced. In other words, p and q don't have any common factors. It is easy to understand that this extra condition in general is satisfied. Because if we had a situation where p and q can be reduced, that means they have a common factor, well, then we simply reduce the fraction by this common factor, end up with a version p over q which cannot further be reduced. Remember that what we want to prove is the fact that the square root of 2 cannot be represented by a fraction p over q. This is why we assume the opposite in order to build the indirect proof. Now let's walk through that proof step by step. We begin by multiplying that equation by q on both sides. This results in this equation. Then we take this equation and take the square of each side of this equation. This results in this second equation. We point out at this stage that the only property we use of the number square root of 2 is the fact that the square root of 2 squared equals 2. This is why, when squaring both sides of the first equation, we will receive the number 2 here on the left-hand side. We conclude that p squared must be an even number, as it obviously contains the factor 2. As a consequence of the fact that p squared is an even number, we can conclude that p must be even 2. But that is not directly clear, so we have to convince ourselves that this indeed is true. So we would like to prove that for any integer number p, if p squared is an even number, then also p itself is an even number. We could do this by creating a general mathematical proof, but for our purposes we will be fine by verifying this fact for the first couple of integer numbers. So 1 squared is 1, and that is an odd number. And in fact, in this case, 1 itself is also an odd number. 2 squared, which is 4, is an even number. And yes, we find that 2 itself is also an even number. 3 squared, which is 9, is again an odd number. And indeed, 3 is an odd number. And lastly, 4 squared, which is 16, is an even number. And yes, 4 itself is also even. If you like, you can try to figure out how a general proof would work for any integer number. Now, let's see where we stand. Based on our original assumption that the square root of 2 can be represented as a fraction p over q, we have concluded that p is an even number. As a consequence, we can conclude that p can be written as p equals 2 times a, where a is an integer number. In fact, this is the defining property of even numbers. Now remember again our original assumption, which was square root of 2 equals p over q. Multiplying this equation by q gives us square root of 2 times q equals p. And by this equation we may replace p in the first equation by square root of q in the second equation. Now for this equation we take the square of both sides, which results in this equation. In the next step we divide this equation by 2 on both sides, which results in the last equation. But the implication of this last equation is that q squared can be represented as 2 times some other integer numbers. That means also q squared must be an even number. And using the same argument as we did in the slide before, we conclude that q itself must be also an even number. Consequently, q has the representation as 2 times some integer number b. So what we have found is that p is an even number and that q is an even number too. Altogether, we obtain this final equation. But what is the implication of this equation? It says that the fraction p over q can be rewritten as the fraction 2a over 2b, where a and b are integer numbers. In other words, that fraction p over q can be reduced because the same factor 2 occurs in the numerator and the denominator. And here we are. This is a contradiction to our assumption. Remember that our assumption was that the fraction p over q cannot be further reduced. Now, as this equation has been derived by a series of logical steps from our original assumption, and as this equation is in turn a contradiction to our original assumption, we must conclude that our original assumption is not true. In other words, it is not true that the square root of 2 can be written as a fraction of p over q. Now we have reached the end of our proof. We have shown that the square root of 2 is no rational number. That means that the square root of 2 is an example for some other type of numbers, which somehow have to lie between the rational numbers. We call those numbers which are no rational numbers, irrational numbers. In fact, the square root of 2 is only one example. There are infinitely many irrational numbers, and indeed there are even many more than the rational numbers. The number system, which consists of rational numbers, that is the fractions, and those irrational numbers, for which the square root of 2 is an example, is called the real numbers, and it is denoted by a capital R. Real numbers can be pictured as making up the complete so-called continuous number line. Each point on the number line represents exactly one real number. The continuous number line contains all rational numbers as well as all irrational numbers. In other words, there is no point on the real number line which is not represented by a real number. This completeness might give us the impression that we have reached the end of our iterating extending of number systems. As you might have guessed, the answer is no. There are still very simple equations which cannot be solved in the real numbers. One example is the equation x squared equals negative 2. And it's no surprise that we cannot find an x such that x squared equals negative 2, because it's a well-known fact that squared numbers cannot be negative, or in other words, that any number, be it negative or positive, when squared will always result in a non-negative number. So you might say that we simply have to accept the fact that this equation doesn't have a solution. But it's exactly the freedom in mathematics, which I told you in the beginning, which allows us to not accept this fact, which allows us to extend the number system of the real numbers one last time in order to even make this equation solvable in the new final number system. Remember when we took the step from the rational numbers to the real numbers? We wanted to work with numbers like the square root of 2, about which we didn't know much except for the fact that its square should be 2. We will now perform a similar step, which admittedly feels a little esoteric. We introduce a new number which we call imaginary or complex unit I, little I. This imaginary unit I should have the simple property that I squared equals negative 1. However, that property only looks simple because at a second glance we know that there is no number which has this property. At least there is no real number. As we already know that this imaginary unit I cannot be a real number, we don't even have to prove it. And this gives us reason to call it imaginary. In other words, the imaginary unit I is the square root of negative 1. Now let us reflect what just happened. As we were unhappy that there are simple equations which cannot be solved in the real numbers, we simply took the freedom to introduce some alien thing called I, which should fulfill an impossible equation. We know nothing else about this imaginary unit I except for that I squared equals -1 and that I cannot be a real number. But what type of number should it be then? That is one funny thing about mathematics, we simply don't care. But although this little I is an alien thing to us, we embrace it with all our mathematical all-day life. In other words, we perform all the well-known algebraic operations to it, which we know from the real numbers. That means addition and multiplication. This results in a new number systems, which we call the complex numbers. We define the complex numbers as all numbers, or we better call them mathematical objects, which have the structure z equals a plus ib, where a and b are real numbers. The reason why they are called complex numbers is the fact that they are composed by two ingredients. The first being a, the so-called real part, the second being ib, where b is called the imaginary part of the complex number z. Note that both the real part and the imaginary part are real numbers. So loosely speaking, complex numbers are the result of the real numbers and this new imaginary unit I being stirred up and mixed together with the result of all possible combinations of the real numbers and the imaginary unit produced by applying algebraic operations like addition and multiplication. Now, while real numbers are illustrated by the number line, complex numbers can be viewed as points in the so-called complex plane. The form of a complex number, z equals a plus bi, is also called the Cartesian form of the complex number. In that sense, the complex number is viewed as a point in the complex plane, where the real part a is the horizontal coordinate and the imaginary part b is the vertical coordinate of the complex number z. So from now on, we can picture complex numbers simply as points in the two-dimensional plane, which can be specified by their two coordinates a and b. Now our journey through the different number systems has come to its end. Well, whenever we have thought that we have reached the end, there was some mean equation popping up which gave reason to another extension of the current number system. So it's a valid question to ask, how can we be sure that we have reached an end? Unfortunately, the answer to this question lies beyond of what we want to cover in that video. But let us point out that within the complex numbers, all equations which are built with algebraic operations like addition and multiplication can be solved within the complex numbers. This fact is so important that it is called the fundamental theorem of algebra. The fundamental theorem of algebra tells us that there won't be any mean equation which we don't know of, which can destroy the complex numbers in the sense as they did it with number systems before. In the next video, we will look at complex numbers, their structures, their different representations, and the ways how we can calculate with them.